Hi, I'm Paul. We're doing Leetcode Must Know interview questions. Today's challenge is LRU cache. Least recently used cache. You probably know what a cache is. LRU is an algorithm for managing cache overflow. We're caching data, but the cache is full. So what happens when we want to add something else to the cache? We're going to have to take something out of the cache. What do we take out of the cache? Well, LRU cache, we take out the least recently used element. So the challenge is to implement an LRU cache class. There's a constructor LRU cache. It takes an integer, which is the capacity of the cache. There's a get method, takes an integer, returns the value of the key, the integer key, if the key exists. Otherwise, it returns -1. We have a put method. Put takes key and a value, so we're caching key value pairs. It updates the value of the key if the key exists. Otherwise, it adds the key value pair to the cache. If the number of keys exceeds the capacity from this operation, then evict the least recently used key. Okay, the functions get and put must each run in O1 average time complexity. This problem is in the linked list category of Leetcode questions. So we can use a linked list. We could use a linked list for the cache, but we can't do get and put in O1 time on a linked list. We could do it with a hash map. We could put the key and index in a hash map. We can do gets and puts in O1 time and then put the key in the cache. But now we've got a problem of changing priorities. Least recently used, most recently used. We want to keep the most recently used element at the head of the at the front of the cache, or the head of the linked list. We want the least recently used at the end of the list. We can't do that with a hash map, and you know, I wasn't sure whether we could do it with the built-in linked list. I mean, I'm looking at the topics here. So we've got hash table or hash map. We've got linked list, design, doubly linked list. The built-in linked list in Java actually is a doubly linked list. So I thought I would try and implement it with the built-in linked list class, because it looks like that's what they want here, that we just write 3 methods. And so I spent about 20 minutes doing that, and then I ran it, and the average runtime for solutions was less than 50 milliseconds. My runtime was over 1,000 milliseconds. I mean, it passed, but it was, I guess obviously not what they wanted. I mean, so there's another way to do this. We can use the hash map and put the key in there and put a pointer to a node in there, a node in the linked list. Now, if we have a pointer to a node in the linked list that we want to move, then we can move it, and it's O1. But we have to create a node class, and we have to create some more methods, and I don't know. It didn't look like that's what they wanted, but it's what we're about to do. To me, doing it that way really elevates it out of the medium grade of problem or at least puts it into the upper echelon of medium problems. But okay, let's give it a try. We're going to need a node class. We're going to create our own linked list. This is our linked list will also be a doubly linked list. So up here we will have a class and we'll call it node. It's going to have an int key and it's going to have an int value. It's going to have a next pointer and it's going to have previous pointer. Oh, we need a constructor. Okay. Node int key int value. This dot key equals key. This dot value equals value. Next. Oh, you know what? I can't do that. This dot next equals null. This dot previous equals null. All right. All right. What do we need in the cache? Definitely capacity. Okay, we need a hash map. We'll do integer and node. Last time I tried this, I just did integer. So we're going to do integer node. Last time I put a linked list in here of integers, but in this case we are creating our own linked list, so we'll just put head and tail nodes. Private node tail. All right. Constructor. It needs the capacity. It needs cache map, right? So cache map equals new hash map. It needs we need no, that's not going to work. We need to set up the doubly linked list with just dummy nodes at the front and the end. So let's say this dot head equals new node, and yeah, these don't really matter. The values. This dot tail equals new node -1. Oops. Anything else? We have to link them together. So this dot head dot next equals the tail, and this dot tail dot previous equals the head. All right, so that is the okay, so that's the constructor. All right, the get the value for a given key. All right, first thing is, if the key doesn't exist, we return -1. So we can say if not cache map contains key, then we'll return -1. All right. If the cache map does contain the key, then we'll use the key to look up the corresponding node in the cache map. So cache map dot get key. Okay. Now, because we just looked that up, that now becomes the most recently used node. So we'll write these methods shortly, but removes the node from its current position in the linked list. And we can do that in O of 1 because the cache map now, the key points to the node. So we have a pointer to the node, and because we have a pointer to the node, we can remove it from the linked list in O of 1, add node, add puts the node at the front of the list. Okay? And then we'll return node dot value. That's what we called it, right? Yes. Okay. Good. All right, let's see how the put works. Put takes key and a value. First thing we want to find out is that key in the cache? So if cache map dot contains key then well, again, let me think about this for a second. If the key is in there, we are going to have to change the value. The easiest way to change the value is really just to remove the node and put a new node. Is that really the easiest way to do that? Yeah, it is. Remove cache map dot get key. All right, so that'll get the node and it'll remove the node. All right, create a new node. Node is going to be a new node with the key and the value. Key and the value. Add it to the cache. Cache map put key node and add node, which we haven't written yet, but it's going to, because that node is now the most recently used, it's going to put it at the front of the list. All right, the other thing that we have to consider here, actually, in this case, do we need to, yeah, we do. Okay, yeah. So what's happening here? If the key is already in the cache, then we're going to remove that node. And in either case, whether it's in the cache or it's not in the cache, we're going to create a new node for the key and value, and we're going to use the hashmap.put. Put, the way it works on a Java hash map is if that key is already in the map, it'll just update the value. If that key is not in the map, it'll add the key and the value. So we have to consider at this point whether or not we went over the size of the cache. If we did, then the node that we want to delete, node to delete, is the last node in the list. It's the node right before the tail node. Okay, remove, again, we haven't written that yet, node to delete, and then take it out of the cache map. Cache map dot remove node to delete dot key. All right. It's not in the cache anymore, so it can't. Yeah. How am I trying to explain that? Yeah, the node is not in the cache anymore, so the key should not be in the cache map. All right. Got too many brackets here for some reason. That looks about right. What does that match up with? All right, so we got that, we got the okay, and the class. All right, that's fine. We need the remove and the add methods. All right, let's do, I don't know, let's do remove. Private remove. It's going to remove a node from the list. Oops, private void remove. Give it a node and it will be removed. Okay. This is good. This is O of 1 because we got a pointer right to the node. So we can say node previous node equals node dot prev. So that points to the node before the node that we want to remove. Node next node equals node dot next. That points to the node after the node that we want to remove. And we'll say previous, whoops, no, that's right. Previous node dot next equals next node. So that just jumps over the node that we're going to remove, and we'll say next node dot previous equals previous node. That also jumps over the node that we just removed. All right. Now we need an add. Okay. Let me just copy the method signature here. Private void add node. Okay. Adding the node. Okay, so we want to add this at the front of the list. We got a node here. It's got to go at the front of the list. All right. Node. Next node equals head dot next. That is that will point to the head dot next will point to the current first node in the list. Okay. Head dot next, which we just saved in next node, will now equal the node. Node dot previous will equal the head node. Node dot next will equal next node. And what about next node? What else do we have to do with next node? Oh yeah, we got to point it back. Next node dot previous will equal the node that we just added. All right. And close that. Okay. I'm going to run that. It's a lot of typing. That can't work the first time. Yeah, good. 35, 36. Why do I have so many semicolons in the middle of node? 35, 36. Remove. Node. 35, 35. 37. Okay, I need that here. Is that it? View more? There's more? 52. Is that missing a semicolon? 52. Yes, it is. All right. Run it. Accepted. Okay. Now we're going to submit it and see what kind of timing we get on it, provided that it actually runs. Oh my gosh, look at that. Okay. Yes, I think I already mentioned, this doesn't even go out that far. When I ran it the other way with the Java built-in linked list, I was out here at over 1,000 milliseconds. That was in the 5th percentile. 5th means 95% of the submissions were better. Actually, even this one, really? This only beats 40%? Okay, but it looks, yeah, 47. Ah, man. I'm edged out here by like 3 milliseconds. Okay. Anyway, that to me is a hard problem. You really can't do it in 01 with the built-in linked list structure in Java. Maybe in some other programming languages you can, even though the Java linked list is a doubly linked list, but it's obviously not implemented in such a way that you get any of the benefit of that, in the way that you do by implementing your own doubly linked list. And that's it. The key improvement was this, mapping the key to a node directly in the list so we can do everything O of 1. And I guess that's it. So anyway, thanks for watching. Please feel free to like, subscribe, comment, and see you next time.